Thank you for inviting me to speak today. I am sorry I could not be there in person with you, but I am hopeful that this presentation will provide sufficient information on the work that TEDx performed to uncover the science behind the endocrine disrupting chemicals on the new SIN list 2.0. Almost exactly a year ago, ChemSec approached TEDx with a request to assist them in gathering information and assessing potential endocrine disruptors for possible inclusion in the new SIN version of the SIN list. TEDx is a US-based non-governmental organization that compiles and disseminates scientific research on the health and environmental problems caused by endocrine disrupting chemicals. We are funded by private foundations, government grants, and individual donors who support our work. TEDx was founded in 2003 by Dr. Theo Colborn, an environmental health analyst who is well known for her groundbreaking work on endocrine disruption. In fact, in 2008, she won the Swedish Gothenburg Prize for the Environment and Sustainability. There were 3 of us at TEDx who worked on this project: Dr. Colborn, Dr. Lynn Carroll, our senior scientist, and me. The fit between ChemSec's needs and the work of TEDx was ideal in many ways. It coincided with similar work we are doing to compile our own list of endocrine disruptors. In fact, we just released the TEDx list of potential endocrine disrupting chemicals. The TEDx list currently contains approximately 800 chemicals. Every chemical on the list has 1 or more verified citations to published, accessible, primary scientific research demonstrating effects on the endocrine system. Despite having just released this list, already we have found many more chemicals to add to it. This is an ongoing project, and we plan to keep adding chemicals as we uncover more research and new studies are published. The TEDx list is now available on our website, which you can see on the slide. We hope that it will be a valuable resource for individuals, governments, industry, and other organizations evaluating chemicals for their endocrine disrupting properties. And thank you, ChemSec, for encouraging us to promote our new release at this event. Now I'm going to walk through step by step the process we used to evaluate the chemicals that ChemSec was considering for inclusion in the SIN list 2.0. The overall approach was basically to get every available study on a particular chemical through a thorough literature search, to weed out the ones that were obviously not appropriate through screening and abstract review, and to select the studies that provided the best indication of endocrine effects. Keep in mind that endocrine effects include direct effects on traditional endocrine glands, their hormones and receptors, such as estrogens, anti-androgens, and thyroid hormones, as well as signaling cascades that affect many of the body's systems, such as reproductive functioning and fetal development, the nervous system and behavior, the immune and metabolic systems, the liver, bones, and many other organs, glands, and tissues. The first step in our process was to conduct a thorough literature search on the chemical names. Some chemicals have what Dr. Carroll has described as a dizzying array of different names. It was important to us that all of them be included in the search logic. For this, we went to ToxNet, which is managed by the U.S. National Library of Medicine and is a collection of databases on toxicology, hazardous chemicals, environmental health, and toxic releases. From ToxNet, we acquired a list of synonyms for each chemical, and using that list, searched the PubMed database for studies containing any of the synonyms. For those of you who don't know, PubMed is a free online service of the U.S. National Library of Medicine that includes over 20 million citations for biomedical articles. Once the search for a chemical name was completed, we downloaded all the references and their abstracts to an in-house database. For one single chemical, this could be thousands of citations or as few as 10. Next, we took that internal database and for each chemical performed a search for all the terms you see listed on this slide. We used terms representing glands and organs like testes, thymus, and prostate, terms representing species like rat, guinea pig, and woman. We also used terms for hormones like estrogen, insulin, and testosterone, and many other terms such as Sertoli and Leydig, fetus, reproduction, and fertility. The little stars you see by many of the words on this slide are called wildcards. They indicate that any letter or string of letters could occur in place of that star. So, for example, searching for star estrogen star would return all the studies with the word estrogen, estrogens, estrogenic, estrogenicity, anti-estrogen, anti-estrogens. You get the picture. Our goal at this stage was to be as inclusive as possible. While there's no guarantee that we found every available study on each chemical, for a study to escape our search process, it would have to not have any of the terms you see on the slide in any PubMed search field, including the title, abstract, and keywords. For some chemicals, even with this inclusive process, we found only a few studies. For these chemicals, additional searches were conducted using Web of Science and ToxLine, which are two other systems that allow online searching of research databases. Next, we manually went through the titles and abstracts to remove items that were obviously not peer-reviewed primary research related to biological health outcomes. For example, we removed review articles, conference proceedings, and letters to the editor. Examples of items not related to biological health outcomes include studies on pest control or remediation, which is removal of contaminants from the environment, studies of analytical methods for determining residues in tissues and fluids, and toxicokinetic studies that only looked at metabolic fate. At the next level of screening, the abstracts for each study were read thoroughly. This slide shows a few chemicals for which we had the most abstracts to review. The number of abstracts for a given chemical ranged from 345 down to less than 10. This level of screening was similar to the initial screening in that we weeded out studies that were not peer-reviewed primary research related to biological health outcomes. It was also the point at which many of the human epidemiological studies were removed from the list. Most of these were removed because they were based on retrospective self-report, they failed to control for simultaneous exposure to other chemicals, or they were unable to report any measure of exposure dose. Next, the studies that passed the abstract review level of screening were downloaded for full review. In this step, downloaded studies were read carefully, sometimes by 3 different members of our team. For each chemical, our goal was to determine if there was any research demonstrating endocrine disrupting properties, and then select the studies that provided the strongest support for endocrine disruption. The best studies had robust experimental designs and sound statistical methods. They were clearly and logically written, with no inconsistencies between the abstract, the text, and the tables. The best research also used both negative and positive control conditions. That means the effects of the chemical were compared to 2 other conditions. One with no chemical exposure, which is the typical control or placebo condition, and one with exposure to a known endocrine disruptor, the positive control condition. Endocrine effects were also evaluated with regard to dose. High-dose studies with high mortality rates in subjects or offspring were avoided, as the effects would likely be from overt toxicity. Studies showing effects of low-dose exposure on function, not just organ weight, were preferred, as they represent the hallmark of endocrine disruption. We also evaluated the overall body of literature for each particular chemical, and tried to include studies from different research teams where possible. We took great pains to accurately transcribe results from each of the selected studies into the database, giving enough detail without rewriting the entire results section. Above all, we avoided including any interpretation of the findings. Then, every Friday, for several months, we took a couple of chemicals at a time, and the 3 of us sat down together and discussed the findings. We discussed where and when the effects were found, asking questions such as, were the effects really endocrine related, or were they effects of toxicity? Was the assay appropriate? Were there any in vivo studies or studies in other species? Was there research at lower doses? It was not unusual to read a study in which the authors never mentioned endocrine disruption. despite findings that were clearly related to the endocrine system. In cases where we had doubts, we called other experts, primarily endocrinologists, to verify that the effects were endocrine related, particularly for studies using newer innovative assays. Through this process I just described, we pared down the wealth of research we started with to the final database we sent to ChemSec, and that essentially concluded our part of the work on this project. In closing, I would like to say that the more we learn and understand about endocrine disrupting chemicals, the clearer it becomes that endocrine disruption will be the health issue that defines the 21st century. At TEDx, we are grateful for the opportunity to add our knowledge and expertise to the process of understanding this complex problem. And we thank all of you for your part in taking it to the next level. Thank you.